Okay, well, hello and welcome. We'll get started. So it's week 6, Wednesday, and just a reminder. I think, well, I don't know if I told you. No class on Friday. Okay, so we will not be meeting on Friday. I have a stats department faculty meeting on Friday, and it's all day, and so I have to cancel Friday's class, okay? So I won't see you Friday, but we'll see you Monday. And then you have a midterm exam 1 week from today on Wednesday, okay? So I have also posted homework 4. So homework 4 is due 1 week from Friday, but I recommend that you finish homework 4 before the midterm, because I think doing homework 4 will be good preparation for studying for the midterm. So that's what I recommend. Okay, so do homework 4. It's it will be helpful. Okay, I've posted this file, midterm 2 topics. So our midterm is Wednesday, 1 week from today, and you'll take it right here. 45 minutes plus or minus plus 5 minutes for passing out papers and collecting. I'll create a seating chart again, and then you can bring 2 sheets of notes, front and back, and then bring a calculator. Okay? All right, so these are the different problems that I've done. So one is random number generation with convolutions. So I'll provide you a small sample of random values. Maybe they're either random uniform or random normal values, and I'll kind of round them off to a couple decimal places, just so you're not dealing with a bajillion decimal places, right? And then what you'll do is, using the provided values, you'll use a convolution to make a random value from another distribution, right? Some random values might require exponential values, right? And you would use inverse CDF method to do that. And these are kind of potential distributions that you might have to use to generate values from, either binomial, chi-squared, t, gamma, beta. I think all of these have been covered in your notes. And so, just make sure you include a few lines of instructions on how these things work in your notes, okay? This should be, problem 1, I think, should be pretty straightforward. Problem 2, rejection sampling. I'll provide an arbitrary target distribution, and I'll also provide an arbitrary proposal distribution. And you will have to find the optimal constant m. M is the constant that we multiply by the proposal distribution, so that m times g of x is always greater than or equal to f of x for all x, right? And so that's going to either require some calculus or maybe a little bit of thinking to figure out that m. And then I will also provide some random values generated by the proposal distribution. So I'll say the proposal distribution has produced these values. Each proposed value will be paired with a random uniform value, and you'll have to tell me whether we should accept or reject that proposed value. Okay. I think this second part's straightforward. Finding the optimal m, that could be tricky depending on, I guess, how comfortable you are with maybe either the calculus or math involved. Maybe some geometry, I don't know. Okay. All right, number 3, we will have a Metropolis algorithm, discrete case. I'll provide a target PMF, so it'll be a discrete case distribution. And I will also specify how new states are proposed. So So in the island hopping example, we flipped a coin, and if it was heads, you went to the right, or it went to the east, and if it was tails, you went west, or something like that. We'll say you've got another method for proposing new states. May not be necessarily exactly the same as flipping a coin. Maybe you spin a spinner, and some parts will be like you go one state to the east or two states to the east or something like that. Okay, so it'll be a little bit different. You'll have a different proposal distribution. Okay. And based on that, using the proposal distribution along with the target PMF, you will figure out the transition probability matrix P. All right, so you'll go it'll be, n by n transition probability matrix for however many states you are possible. And then I will say, if you have some distribution at time t, if this is the probability distribution at time t, what is going to be the distribution at time t plus 1? Well, you basically just do some multiplication there. That will be problem 3. Okay, and then the last problem will be Metropolis algorithm, the continuous case. And here I will have a continuous PDF as our target distribution, and we will have the proposal distribution will be a normal distribution with mean at the current location x at time t, and I will provide some arbitrary sigma value. Okay, and I will provide an arbitrary starting location x at time t. And you would perform 2 iterations of the Metropolis algorithm, okay? So for each iteration, I'll provide a random U1 and a U2, both of them come from the uniform distribution. You'll use U1 and inverse CDF method to find the proposed value of x, okay? And I will provide a standard normal CDF table. So, and you will use that to perform inverse CDF method. Does that kind of make sense? So if your U1 is 0.5, your proposed location is going to be x at time t, right? And if your U1 is, say, 1.96, I'm sorry, not 1.96. If your U1 is 0.975, if the random uniform value is 0.975, then the proposed location will be x at time t plus 1.96. And if your u was, say, negative, 0.1, if your u is 0.1, what is the inverse CDF of 0.1? Now I don't know. Well, that's assuming a sigma of 1. And so, if the sigma is, say, 2 or something like that, right? So Q norm of 0.1 gives you negative 1.28, okay? So your x at time t, your proposed location will be x at time t minus 1.28 times your sigma. I feel like I'm getting away too much already. Okay, and then you'll figure out the p move. You'd have to show your work for that, and then you'll use U2 to decide whether or not you will move to this new location. All right, and that will be it. That's, I think that will fill up 45, 50 minutes of time there, these 4 problems. Okay? Any questions? Yes?
What does homework 4 do?
When's homework 4 due? Homework 4 is due 1 week from Friday. So you got like 10 days to do it. Or 9 days? I don't know. What is? It says 9 days and 7 hours. But I think you should try to do it as part of studying for midterm 2. Okay. All right. So today for lecture, I wanted to do maybe a little bit of a kind of a proof here to show how, like, kind of why the Metropolis algorithm works, and actually we'll show the generalized form, And this is called the Metropolis Hastings algorithm. You know what? Where is... All right, so let me just write this down.
Is this legible? Okay.
All right, so the Metropolis Hastings algorithm is a generalization of the Metropolis algorithm. Okay, so for the Metropolis algorithm, the proposal distribution must be symmetric. Okay, and what we mean by that is we're going to say that g of proposing the value x prime, given that you are at location xt, this has to be equal to the probability of proposing xt, given that you are x prime. Okay? That is to say, the probability of proposing x prime if we are at state xt, this value is equal to the probability of proposing xt if we are at state x prime. Okay, so the idea here is to draw a normal distribution. This is not a good looking normal distribution. This is kind of hard. Is here I'm centered at xt, and I'm going to propose x prime. Whereas if I were centered at x prime, the probability of proposing xt is the same height, right? These two probabilities are equal because g of x is symmetric. Oops, let's see. Okay, so that's the Metropolis algorithm. The Metropolis Hastings algorithm loosens this, okay? This does not require that the proposal distribution is symmetric. And that is to say, g of x prime given xt is not going to be equal to g of xt given x prime. Okay, so how does this work? Well, the Metropolis Hastings algorithm, so I'm going to just abbreviate this, the MH algorithm, works very similar to the Metropolis algorithm. It's just that the proposal distribution, not necessarily symmetric. Okay, so number one, you pick an initial state x at time 0. Okay. We also have a target probability distribution P of x. And then we iterate. Okay. So step 2a, we will propose a candidate location, candidate state, x prime, coming from g of x prime given xt, okay, based on current state x. Okay, so we propose a candidate state x prime, and then we will calculate the acceptance probability. Which we'll call P move. And this is equal to the minimum between 1 and we have P of the proposed location, x prime, divided by P of the current location, x at time t. So this is the same as the Metropolis algorithm. And then the Hastings part is we also multiply it by the difference between the two proposal distributions. So we're going to say, well, what is the probability of proposing xt if we're located at x prime versus the probability of proposing x prime if we're located at xt. Okay? So this part over here, if we dropped this, if it's symmetric, this just reduces to 1, and then it becomes the Metropolis algorithm. Okay? But if it's not symmetric, if g of x is not symmetric, then you have to include this factor in there. So 2c, you would accept or reject the proposed location. Proposed state xt, or not xt, proposed state x prime. And to do that, you generate a u from the uniform 0 to 1, and if u is less than p move, except, and that means x at time t plus 1 will be x prime, the proposed location. If u is, we'll say less than or equal to, if u is greater than p move, reject. And x at time t plus 1 will just be a repeat of x at time t. Okay. Also note, technically, you don't actually need to know p of x directly. If p of x is unknown, you can use f of x proportional to p of x. All right. Is that okay? Feel good? All right. Did I give you your review quiz answers yet? First one? Okay, first one today is E. E as an elephant. E as an elephant is our first review quiz answer. All right, so what I want to show you is that this Metropolis Hastings algorithm, and if the Metropolis Hastings algorithm, which works in this generalized case, will also, if the Metropolis Hastings algorithm works, then the Metropolis algorithm also works, because Metropolis algorithm is the same thing as the Metropolis Hastings, it's just this is reduced to 1, okay? And I want to show you that this thing works because at the target distribution we have detailed balance. At the target distribution p of x, we have detailed balance. And what is detailed balance? So if you remember that animation where we had like the dots flowing from California to New York and the dots flowing from New York to California, do you guys remember that animation? You have detailed balance when basically the amount flowing in this direction is equal to the amount flowing in the other direction. And detailed balance is achieved when all of the states, so even if you have like 1,000 states or infinitely many states, is that every pair of states has detailed balance, that the amount flowing from one state to this state is the exact same as the amount flowing from that state back to this state. So you're kind of at this equilibrium where nothing is changing once you're at your kind of target distribution, okay? So that is to say that if you have some state xt and some state x prime, we want to say that the amount flowing from xt to x prime is exactly equal to the amount flowing from x prime to xt. And don't worry, this is not on your list of topics that you need to know for the exam, but it's on the list of topics that are good to know to have a better understanding and appreciation for Markov chains. So the amount flowing from xt to x prime is exactly equal flowing from x prime to xt, okay? And this will be true for any two states, okay? Any two states, if all states follow the target distribution, P of X. Okay, so everything follows this target distribution that we want to achieve. Once we have this probability laid out, then we will have detailed balance, okay? So we will just kind of, you know, by definition, we say the probability of X, this is equal to the probability of being in state X in the target distribution. Excuse me. Okay. And then we have probability of x prime given xt. This will be the probability of transitioning from state X to state X prime, given that we started, given that we are already, that we are in state xt. Okay, so what we want to show that the amount flowing from xt to x prime is equal to amount flowing from x prime to xt. Okay, so the amount flowing from, there's my little strange dot there. Okay. The amount flowing from xt to x prime will be, first we have to start off at state xt, so the probability of starting in xt multiplied by the probability of transitioning to x prime given that we started in xt. And we want to show that this is equal to the probability of starting in x prime and then transitioning to xt given that we started in x prime, right? I label this, so this will be probability of starting in x prime times catch up on your copying. This is also all saved, so if you're just sitting and watching, don't worry. I'll post it. I'll post it online. Okay. So we have that. Okay. Well, here let's just start off with the trivial case. Okay. If the proposed location is rejected, then kind of the next state, x prime is equal to the current state xt, right? So our the next state is our current state, and so both sides of the equation are equal. I mean, there's effectively no flowing, right? So you don't have to worry about like, is there balance between this state and the next state? It's just, there's no flow. So that's kind of the trivial case. But really what we want to see is like, okay, if there is stuff flowing from say state xt to x prime, right? The proposed location is somewhere different, and we end up going there, we want to show that that is the case. All right, so on one side, I'm going to just draw a line here. And we want to show that these two sides are equal. So on one side, I've got probability of starting at xt times probability of going to xt, given that we started at xt, and we want to show that this is equal to the probability of x prime, given that we and probability of going to xt, given that we started at x prime. Okay, so this is what we want to show. Okay, so this over here is going to be probability of xt, and this probability of going to x prime, given that we started at xt. This is going to be, first we have to propose using our proposal distribution, g of x prime, given xt. So this is probability of proposing times basically p move. Probability of moving there is the minimum of 1. Probability at the target location at x prime, xt, times from the Metropolis Hastings, g of xt or g of x prime xt. I hope you guys can read this. Let me just clarify this. This is a x prime. Okay, so it's the probability of proposing this location using your proposal distribution multiplied by the probability of p move. And p move is the minimum between 1 and this quantity. Okay, and so what I'm going to do in the next step is we distribute g of x prime given xt through the min function. And then what I'm also going to do is replace 1 with p of xt divided by p of xt. Okay, so if I do that, then this becomes probability of xt times the minimum of, and I'm distributing the g of x. Okay, so I'm going to replace 1 with p of xt divided by p of xt, so that's still equal to 1, times g of x prime given xt. Okay, so we want to test the minimum between that and I'm going to distribute this through here. So I've got p of x prime divided by p of xt times g of xt given x prime divided by g of x prime given xt times, and I'm distributing this, g of x prime given xt. Okay. And these two things, this part down here will cancel with this over there. Is that okay? And then I'm going to go ahead and distribute. Oh, do I need to pause? Or are we okay so far? Okay, and then we'll go ahead and distribute this. So now we get, this is equal to the min of, so I've got p of xt times p of xt divided by p of xt times g of x prime xt times p of, okay, comma, p of xt, p of x prime, p of xt times g of xt given x prime. Okay, and then so these things all cancel. I guess technically it wasn't necessary to replace the 1 with p of xt over p of xt, but whatever. Okay, so over here I've got min, the probability of going from xt to x prime given xt is going to be the minimum between p of xt times g of x prime given xt. This is the amount kind of flowing, versus p of x prime times g of xt given x prime. So, parentheses there. So I've got that. Okay? Basically, we're going to do the exact same thing on the other side, and I'm going to just go through this part really quickly. I'm not even going to bother explaining my steps because it's pretty much the same thing, except I've got x prime swapped with xt's. Okay, so if I do this, This is messy over here. Okay, so I'm basically following all of the same steps. And if you follow all of the same steps, and you do all of these cancellations over here, you also end up with the minimum between p of x prime times g of xt given x prime and p of xt times g of x prime given xt. Okay? And so if you look at these two things, these are equal. So when we map out, or when we figure out what is the probability of going from xt to x prime, and we say, what's the amount flowing from xt to x prime, and what's the amount flowing from x prime to xt, because of the Metropolis Hastings algorithm saying, we're going to take the minimum between 1 and this ratio between x prime and xt, the kind of the flow rate ends up being exactly equal to each other, right? Because the acceptance probability of going to a lower probability state is exactly equal to kind of the relative ratio between the lower probability state and the higher probability state. And so because of that, this we have detailed balance, that the amount flowing from one state to the other, and any two states, x prime and xt, there's infinitely many of them in a continuous distribution, but if we just think about overall on the chain, what's the probability of going from one state to another state and another state to another state? All of them are going to be in detailed balance when we're at that stationary distribution. And so when you allow the Markov chain to run long enough, according to kind of the ergodic theory, we're eventually going to reach this stationary distribution. And at the stationary distribution, we have achieved what we want, which is we're going to produce values in accordance to our target distribution. And so that's kind of this really, I think, neat thing about the Metropolis algorithm and the Metropolis Hastings algorithm, is that even if you can't figure out the target distribution directly, you can get something proportional to it, okay, and it still works out. And even if you don't know where a good starting location is you can just let it run for a really long time, and it will eventually find kind of a good location to sample values from. And the values that it samples from will be in accordance to the target distribution. Okay, so this is to just show that these two sides, if you go through all of this work, are indeed equal to each other, okay? It's the minimum between this value and this value, and this side is also the minimum between the same exact two values. And so therefore, it has to be the same thing. Okay. Do I still need 2 quiz answers to give you? Okay, the last 2 are D and B. D as in dog, and B as in bear. Second one is D, third one is B. Okay, and that's it. So I will not see you guys on Friday, so have a good rest of your week, good weekend, and I'll see you guys on Monday. All right, that's all. Okay, thanks guys.